Hello, Integrated Math 1. We're in a new module. Welcome to lesson 2.1.1a. Yeah, that's right. We're going to be connecting arithmetic sequences with linear functions. We already talked about how arithmetic sequences create linear functions, but we're going to go a step further with that today. So just to get us started, we do have a little warm up here on page M2-7. Please note it's now page M2-7. We're in a new module, module 2. And I would like you to write the first 5 terms of the sequence generated by this explicit arithmetic formula. Go ahead and hit pause, jot it down, and then hit play when you're ready to check your work. So hopefully you're remembering, taking it back a little bit to our unit on sequences, where we said the arithmetic explicit formula, if I wanted to find the nth term, we did the first term plus our common difference times n minus 1. So what this means for us is that 10 is clearly our first term, and our common difference is a -3. So if I want to write the first 5 terms, of course, I will start with a 10, minus 3 is 7, minus 3 is 4, minus 3 is 1, minus 3 is a -2. Yay, us. There is another option. You didn't have to do it. I think most of you guys did it that way. But if you wanted to, you could have plugged in 1 for your first term, and then a 2, and then a 3, and then a 4, and then a 5. And of course, you would have gotten the same numeric sequence. So we're making connections between arithmetic sequences and linear functions. That's what we're doing today, guys. And we've got some linear goals. We're actually going to take a couple days to do this just to make sure we get it solid. And we have several learning goals here. So we're going to use algebraic properties to prove that the explicit formula for an arithmetic sequence is equivalent to the equation of a linear function. We're going to relate the defining characteristics of an arithmetic sequence, the first term and the common difference. And we're going to relate those to the defining characteristics of our linear functions, right? Y-intercept, slope. How are these guys related? We're going to be talking about that. We will also connect the slope of a line to what we call the average rate of change of a function, and we'll be hitting that later on. So as we go through the next couple of days, some of the terms you're going to see, the key terms will be conjecture, first differences, average rate of change. It's a big one. That's a big one. We're going to come up in the next couple of days. So you know that all sequences are functions. What type of function is an arithmetic sequence? I'm hoping you remember what type of function arithmetic sequences give us. So as part of our getting started activity over on page M2-8, Kenyatta is counting the number of new flowers that are blooming in her garden each day in the spring. So sequence A represents the number of new flowers. On day 1, she had 3, day 2, she had 6, day 3, day 4, day 5, on and on. She also measures the height of the first sunflower that has started blooming. So the first sunflower, so she's counting how many sunflowers have bloomed, but she's also measuring the height of the very first sunflower. So sequence B represents the height in centimeters of the sunflower on day 1, day 2, day 3, day 4, day 5, on and on. So on day 1, the sunflower was 3 centimeters tall. Day 2 was 6 centimeters, 9 centimeters, 12 centimeters, 15 centimeters. You get the idea. So you now have 2 sequences. I have a few things I want you to do. For each sequence, first, determine whether it's arithmetic or geometric. Second, write the explicit formula. And you may have to run back real quick to our previous unit, unit 1.2. Write the explicit formula that generates the sequence. And then the third thing I want you to do is I want you to graph your sequence. Ooh. Go ahead and hit pause to work all this out, and then hit play when you're ready to check your work. So to start off with, it looks like it's doubling every time, right? 3 times 2, 6 times 2, 12 times 2, on and on and on. So that to me says, since I'm multiplying by 2, that it is geometric. Since it's geometric, hopefully you remember, sorry, I've been plunged into darkness. Hopefully you remember that the deal was that when you did your geometric formula, it was your first term times your common ratio to the n minus 1 power. Well, my first term's having issues. I can see my first term is 3. We said it was doubling each time, right? Times 2 times 2. So it looks like my first term is 3. By multiplying by 2 every time, my common ratio is 2. So here's my formula. Yay. So there is my lovely formula. There it is. Now, there it is, all pretty and typed. Yay. We have also been asked to graph it. Okay, I can do that. So on day 1, there were 3 blooms. So day 1, looks like we're counting by 2s, right? 2, 4, 6, 8, 10. Yeah. So on day 1, there were 3 blooms. On day 2, there were 6 blooms. On day 3, there were 12 blooms. On day 4, there it is, there were 24 blooms. So 4, 22, 4, excellent. Wow, okay. And on day 5, there were 48 blooms. So here's 5. I'm going to go all the way up to 40 and not quite to 50. Oh my goodness gracious, this is crazy. So I plotted my points. Good job, me. For sequence B, this was how tall the sunflower was getting. So 3, 6, 9, 12, 15. It looks like we're adding 3 inches every day, right? Every day our sunflower is 3 inches taller than it was the day before. So that means it's arithmetic, definitely arithmetic. And so if you recall, we were just talking about this. Our arithmetic explicit formula was a sub n equals a sub 1 plus d times n minus 1. So fine, I can see that my first term is 3. My common difference is also 3 though, right? Because I'm adding 3 every time. And there's my explicit formula. Hooray! There it is, all pretty and tight. Of course, we are also asked to graph this one as well. You know what? I might use a different color. I'm going to use a different color just to make it a little easier to see. So if I graph my sequence B, on day 1, we also had 3. Oh, so it's the exact same spot. On day 2, we also had 6. So again, the exact same spot as before. But here's where it goes a little different. Day 3, we're up to 9. Oh, so not as much. Day 4, we're up to 12. Below that guy. And day 5, we are up to 15. So 10, 2, 4 and a half. Oh dear, sorry. Whoa. Yeah, my blue line is not going up as fast as my red line was there, was it? And we knew that. Geometric sequences are exponential, right? They get bigger a lot faster than our poor little arithmetic guys who are just linear. They can't keep up. Can you list at least 3 common characteristics of the graphs and then kind of compare our 2 sequences? Go ahead and hit pause, jot down your thoughts, and then hit play to keep going. So some of the characteristics I noticed, both graphs started at x equals 1. Both graphs are discrete. I noticed that, right? They're dots. They're not like solid lines or solid curves. I noticed both graphs are increasing, right? And I also noticed that both sequences have the same first 2 terms. Did you notice they both started with 3 and 6? I noticed that too. But of course, our arithmetic sequence builds by common difference and the geometric sequence builds by common ratios. It's a little different, right? There's a difference between adding and multiplying. We know this. So with this in mind, now that we've graphed one of these, I have 4 explicit formulas for you over on page M2-9, each representing a different arithmetic sequence. You can see we have different we have different first terms, we have different common ratios. So with this, here's what I'd like you to do. I would like you to take these 4 explicit formulas, and I would like you to match them with your graphs. Got 4 formulas, 4 graphs. Can you match everybody up? See what you can do with this. And again, as far as strategies you use, I would maybe start by looking at the first term. Good place to start. Then I'd look at the common difference. Go ahead and hit pause to match all these up, and then hit play when you're ready to check your work. So I'm looking around here. I'm looking at this first equation, and I see it has a first term of 2. So I'm not going to pick this one because that's -4. Ooh, that one has a 2, so this is a possibility. Oh, graph C also has a 2, so it's also a possibility. Graph D's first term is at 4. Great. So I've narrowed it down to B and C because they both start with a first term of 2. And then I looked further and realized that we were subtracting 4 as our common difference. It should be going down 4. Oh, graph B goes down 4 each time, doesn't it? Graph C doesn't. Graph C looks like it's going up 4. So you know what? I think that this first arithmetic sequence needs to go with graph B. Feels fair to me. I'm going to look at the one just below it here. So I have a sub n equals -4 plus 2 times n minus 1. So my first term is a -4. So the first thing I'm going to do is I'm going to look at these 4 graphs. Pardon me. I'm going to look at these first 4 graphs. You know, you said bless you in your head when I sneezed. And I'm looking at this thinking, well, the first term is a -4. You know what? The only graph that starts with a -4 is graph A. So I guess that's it. Okay. And just to double check, it looks like I'm going up by 2. I have a common difference of a +2. So up 2, up 2, up 2. Yeah. Okay. We're good. Looking at my next explicit formula, I have a sub n equals 2 plus 4 times n minus 1. So again, I want to look for one of the graphs that starts with 2. It looks like graph B and graph C both start at 2. All right, all right. And we're adding 4, so it's definitely not B because that's subtracting. But I can see that graph C is adding 4 each time. So I'm going to say that this equation goes with graph C. And my last explicit arithmetic formula, a sub n equals 4 plus 2 times n minus 1. I have a first term of 4, and if I look, oh, graph D, it's the only one with a first term of 4, so I'll start with that one. And then, of course, I can see we're adding 2 each time, which is good because my common difference is +2. Looking at these lovely graphs that you just dealt with, the set of graphs, I'd like you to identify the function family represented here. So based on all these formulas and graphs, what do you think? Do all arithmetic sequences belong to this function family? Go ahead and hit pause, jot down your thoughts, and then hit play when you're ready to check your work. Well, I hope you caught these were all linear, right? These graphs all belong to the linear function family. And it does say to explain your conjecture. A conjecture is a mathematical statement that appears to be true, but has not yet been formally proven. So yeah, it looks like all of these guys belong to the linear function family. So, you know, I feel like the graph of any arithmetic sequence is linear. That's the impression I'm getting at this point in time. Because both arithmetic sequences and linear functions have that constant rate of change. And some of you guys have mentioned it before. I think we've called it a constant difference in the past, but it is a constant rate of change as well. So let's take a closer look at the relationship between arithmetic sequences and the family of linear functions. You know a lot about each relationship. The explicit formula and the table of values that represents graph C are shown. So here I have graph C, yay. We have the formula, right, from earlier, so that went with graph C. A sub n equals 2 plus 4 times n minus 1. And then we've also got here a table. So we said term number 1 was 2. We said term number 2 was 6. Term number 3 then would be 10. So term number 1 is 2. Term number 2 is 6. Term number 3 is 10. And term number 4 is 14. Can you just take a moment to describe the domain of the sequence? Remember that domain is X. Go ahead and hit pause, jot down your thoughts on that, and then hit play to keep going. So the domain is all my possible X's, and it looks like I've got 1, 2, 3, 4, which means if I kept going, I'd have 5, 6, 7, 8. So I'm going to say the domain of the sequence is all integers starting with 1, also known as the natural numbers. Can you identify the common difference in each of these? Go ahead and hit pause to write out the common difference and then hit play when you're ready to check your work. If you're using the formula, that might be the easiest place to find your common difference, right? Because we have a sub n equals a sub 1 plus d times n minus 1. So if we have this lovely formula, right, that means my common difference is going to be 4. So you could say d equals 4. But you also could have looked at the table, right, and been like, hey, I'm adding 4 each time. My common difference is 4. You also could have looked at the graph and been like, hey, I went from 2 to 6 to 10 to 14. We're adding 4. So our common difference is 4. You can see it here, and we can see it here as well. Can you draw a line on your graph? So right now it's discrete, right? We just have a couple of dots. Can you draw a line on your graph to model the linear relationship? And then can you write an equation to represent that line? Remember y equals mx plus b? Do you remember that? We find the slope and the y-intercept? Yeah. Can you draw the line and use y equals mx plus b to write an equation? Go ahead and hit pause, see if you can do this, and then hit play when you're ready to check your work. So first I used a straight edge to draw a line, and I do recommend using a straight edge to draw your line. It really does make things a lot easier. So here's my nice straight line. We are then asked to write an equation. So I'm going to use the whole y equals mx plus b. And I looked at this and I said, okay, well, b is the easy one, right? B, actually, I'm going to get my red pen back, easier to see. No, there it is. And I can see that b hits my y-axis right at -2. So I'm like, all right, my y-intercept is -2. That's going to be my b. Now the trick is the slope. Please remember that slope is rise over run. We've talked about this before. So I can just pick a point to another point. So from here to here, it looks like I go up 2, 4. So it looks like I'm going up 4. And then I ran. Now be careful when you look at this. I ran from 1 to 2. I ran 1. So it looks like I rose 4 and ran 1. So it does look like my slope is 4. So that means my equation, if my slope is 4, my y-intercept is -2. Y equals 4x minus 2. Yay. But how did this affect the domain? So when we did the domain of a discrete graph, it was just integers. What's my domain now that it's a line with arrows on both ends going forever and ever and ever in both directions? Can you go ahead and hit pause and jot down what the domain is now? And then hit play when you're ready to check your work. So now that it's a line, it can be anything, right? It doesn't have to be 1. It could be 1.5. It could be -7 3/4. It could be anything. So I'm going to say the domain is now all real numbers. It's all real numbers. Yeah. So we talked about an explicit formula before. An explicit formula is one equation that you can use to model an arithmetic sequence, right? Did you know you can rewrite the explicit formula for an arithmetic sequence into function notation? Truly. Check this out. Here we have our lovely arithmetic sequence. But I want to use function notation. So earlier, way back in the first unit, way back in the first unit, do you remember this? How we said that a linear function is usually written as f of x equals ax plus b. You already know b is the y-intercept. So here's what we're going to do. Instead of a sub n, I'm going to rewrite that as f of n. So instead of an, I now have fn. And we're just using an f for function. We used a for arithmetic. Now we're going to use f for function. The other thing is I don't want it to look like this. I want it to look like this. So I don't like those parentheses, so I'm going to go ahead and distribute. 4 times n is 4n. 4 times a negative 1 is negative 4. So now 2 plus 4n minus 4. Wait though. I have like terms. Check that out. I've got 2, a positive 2, and a negative 4. Well, 2 minus 4 gives me, and they went ahead and swapped it around there. 2 minus 4 gives me a negative 2. So now I have 4n minus 2. So instead of a sub n equals 2 plus 4 times n minus 1, it turns out you can turn this arithmetic sequence, do a little distributed property, and combine your like terms, and you now have it in function form. F of n equals 4n minus 2. Which maybe that looks a little familiar to you. Can you compare the equation that we wrote to model the graph and compare it to what we just wrote with our arithmetic sequence in explicit, we're turning our explicit formula into function form? Can you compare the two? Go ahead and hit pause. Tell me what you notice. Hit play when you're ready to keep going. The equation and the function have the same slope and y-intercept. Did you catch that? Yeah. The only difference is that the equation has a y and the function had f of n instead. So instead of y and x, we had f and we had n. But it was the same form, wasn't it? And it was the same numbers that were showing up. Can you just take a moment to compare the common difference with the slope? What do you notice? Hit pause, write it down, hit play to keep going. I don't know about you, but I noticed that the common difference was 4, and I noticed that the slope was also 4. Oh my gosh, guys, the common difference of an arithmetic sequence is the slope of the linear function. So magical. So let's dig a little deeper. So we've got down the slope thing. We're like, hey, the slope and the common difference, they're the same. And so Hank jumps in, and Hank is like, you know what? The y-intercept of a linear function is the same as the first term of the arithmetic sequence. But he's wrong. Why? What's wrong with Hank? Go ahead and hit pause. Write down what's wrong with Hank's reasoning, and then hit play when you're ready to keep the discussion going. So, yeah, Hank's reasoning is incorrect, and here's why. Remember, the first term of the sequence is term number 1, which means that's when x equals 1. But the y-intercept is when our x equals 0. So that's why Hank's a little bit off there. Our first term of the sequence is actually when x equals 1, but the y-intercept of a linear function is when x equals 0. So Hank just got a little confused, got a little bit off. But good on him for trying. As always, guys, I hope you found this helpful. I hope you found this useful. If you got questions, concerns, please email me or come see me during office hours, during lunch, something. Come talk to me, and I'll see you guys later. Bye.